YouTube viewers, it is Crystal here. In this video, what we're going to do is we're going to compare a parametric test to a non-parametric test, and you can see the results that you get from two tests, one being parametric and the other being non-parametric. So when assumptions fail, data does not satisfy the assumptions required for a parametric test, such as ANOVA t-test or Pearson correlation. Non-parametric tests exist for those instances when assumptions fail, being the statistical safety net. When assumptions fail, parametric tests become unreliable. Their p-values, confidence intervals, and effect estimates can be biased or invalid. Non-parametric tests can be used because they require few assumptions and rely on ranks or parametric versus non-parametric testing. Okay, so as they require fewer assumptions and rely on ranks, or let's see if we get anything else here. And rely on ranks or signs instead of the distributional forms. So what we're going to do is we're going to take two distributions or two types of tests, one being parametric and the other being non-parametric, and we're going to compare the test and see the results that we get. And we're going to do that in base R. So we're going to have a two-sample comparison. So we're going to have the t-test versus the Wilcoxon rank sum. So the first thing we're going to do is we're going to set the seed. The reason why you set the seed is so every time you run the program, the variables will be initialized to the same value. So you type set.seed brackets 1, 2, 3, and you can type any number you want inside the brackets. So we're going to have sample A, which is a normal distribution. So A is a randomly sampled normal distribution. It has 40 samples, has a mean of 0, and a standard deviation of 1. And sample B is a skewed distribution, and this is an assumption violation. So B is a randomly sampled exponential distribution with 40 samples with the rate of 1. And then so this is exponential, and it has a strong right skew. So the parametric test is going to be a two-sample t-test. So t-result becomes t.test brackets A, comma, B, comma, their equal equals false. And we're going to look at the t-result. So your t-result is a Welsh two-sample t-test. The data is A and B. Your t-score is a negative 4.85. Your degree of freedom is 77.889. So generally how they calculate the degrees of freedom is you take the number of samples and then you subtract 1 from the distribution. So you have 40 samples in each in A and B, so that's going to give you a total of 80 minus 2, which is going to be 78. And they've calculated the degree of freedom using an algorithm, which comes up with 77.889, which is very close to 88. The p-value is 6.033 to the negative 6. So that means that the p-value is well below the significance level of 0.05. So the null hypothesis would be that the means are equal, or there's no significant difference between the means. And the alternate hypothesis is there is a significant difference between the means. So since the p-value is less than 0.05, which is the significance level, you're going to have to go with the alternative hypothesis, which is telling you that there is a significant difference between the two means. So you have a 95% confidence interval and negative 0.14 to negative 0.5, and sample estimates. So your mean of x is 0.045 and your mean of y is 1.039. So you can see that the mean of x and y, there's a pretty big difference between the means of x and y. So we've done our t-result. Now we're going to have the nonparametric Wilcoxon rank sum test. So W result becomes Wilcox dot test brackets A, comma, B. And then we're going to look at the Wilcoxon sum rank test. So your Wilcoxon sum rank test, your data is A and B, your W score is 364, your p-value is 1.541 to the negative fifth, which is still really low. It's still less than your significance level of 0.05. So that means you're going to reject the null hypothesis in favor of the alternate hypothesis. So the true location shift is not equal to 0. So the null hypothesis is going to be the location shift is equal to 0. And the alternate hypothesis is the location shift is not equal to 0. So since your p-value in this nonparametric test is less than 0.05, which is the significance level, we're going to go with the alternate hypothesis. So I asked some questions. It said the Wilcoxon test gives a better result because the t-test assumptions are violated by the skewed distribution of sample B. So now what we're going to do is we're going to plot our answers. So we're going to plot the distributions to show assumption violations. PAR brackets M pro equals C, which is a vector of 1 and 2. And then your density plot is plot brackets density A, comma, color equals steel blue, line width equals 2. Main is your title, is density comparison. XLab is the label on the x-axis, which is the value. So then we're going to put some lines in the chart. So lines, brackets, density B, comma, color equals tomato, comma, line width equals 2. Then we're going to put a legend on the chart. So legend brackets top right, so that's telling you that the legend is on the top right. So the legend is a vector being A normal and comma B skewed. Color is a vector with steel blue for A normal and tomato for B skewed. Line width is 2 and BTY equals N. So now we're going to create a box plot comparison. So box plot brackets A, comma B, comma, names is a vector with A normal, comma, B skewed. Color is another vector. So A is still blue and B is tomato. Main is the title, which is box plot A versus B. And Y lab is your label on your y-axis. Is value, and par brackets MF row equals a vector, which is 1 and 1. So we run it. We run the program. And then when we run the program, you see you've got your density comparison. So your density comparison is the value is between -3 and +3. And so blue line is your normal distribution, and the B and the red line is your skew distribution. So you see that your normal distribution is slightly over 0.3 and the skew distribution is a lot higher than 0.3. And now we're going to create a box plot of A versus B. So blue is your normal box plot and B is your red box plot. So the mean or the median of the normal box plot is just slightly over 0, but when we created the randomly sampled normal distribution, we wanted a mean of 0, but this is calculating the median, which is just slightly more than 0, and then the median of the skewed box plot is around 1. So you can see that the means and the medians are different. There's 1 point different. And as a result of the difference between the means and the medians, you're going to have to reject the null hypothesis and go for the alternate hypothesis, which means that there's a significant difference between the two distributions. So that concludes the comparison of the parametric versus nonparametric test. There's other comparisons that you can do as well, but we're only doing one comparison in this video. And as it said in the text, it said the nonparametric test gives you a more accurate result than the parametric test. So sometimes when your data isn't normally distributed, or mostly when your data isn't normally distributed, it's better to use a non-parametric test because you're going to get a more accurate result. So that concludes this video. And the next video, we're going to do another video on non-parametric test. And so I hope that you watch the next video, and I hope that you've got meaningful information out of this video. And see you in the next video.